This is our first 6 weeks quiz on operations, compositions, and inverses mainly. And this is problems number 1 and 2. These two items here, this table representing the function g of x on the left and this graph representing the function f of x on the right, relate to problems 1 and 2. Okay, problem 1, find f of g of 3. First of all, this g is adjacent to the 3, and so we go to the g function first, and we look up 3, and we see that for an input of 3, we have an output of 7. And so we take that output of 7 from g and go up here to 7 on the f and go straight up to the graph, and which aligns us with an output of 8. So our answer to problem number 1 is D, 8. Next, we're going to look at problem 2, find g of x of 2. Well, this time we have the 2 adjacent to the f, so we go to the f function and go up from 2 to the graph, and that lands us over at an output of 3. So we take this 3 and come around to the table, the g of x table, and we see that for an input of 3, we have an output of 7, therefore g of f of 2 is equal to 7. So those are problems 1 and 2. Next we go to problem 3. What is the range of the function g of x graphed below? Well, the range, as you may recall, I hope you recall, is going to be the y value. And so what we see is the function starts its range here at 4, and so that would disqualify C as a correct answer, likewise A. And so really we're talking about the distinction between the parentheses in answer B and the bracket opening in answer D. Well, the open point means, in this case, greater than, not greater than or equal to. And so our correct answer is B. Next, we go to problem 4. Jaime kicks a soccer ball at an angle from the ground. The altitude of the ball in meters given by the function f of t equals 35t minus 5t squared, which number is closest to the maximum height of the ball. And for this, I planned a little bit ahead by going to entering the function in the graphing calculator, that function being f of x equals 35x minus 5x squared. And here we see the function graphed in the standard window. We don't come anywhere near seeing the height, but we can look back at our table, and our table tells us our maximum height that's possible given these answers is 75 meters. So we can go set that just a little bit above 75 meters. Maybe if we go to here we are, 80 meters in height. Let's go to the menu, and we're going to go to 4, Window Zoom, Window Settings, and we're going to keep everything the same except we're going to get our Y maximum at 80. To be sure, we're going to get the top of that function, and we come down to Tab, press Enter, and here we are. We see a nice graph, and what is the height of this downward facing parabola? Well, for that, we can go to Menu, Trace, and we can use Graph Trace, and if we, here we see the cursor at the origin. If we graph trace, we can go right up to the top, and there we have a maximum. The maximum, it shows the maximum right here. There we go. There was the maximum that flashed briefly, and that maximum is at 3.5. comma 61.3. I think it's really going to be 61.25 anyway. That would give us a maximum height of, our best answer in this case would be 61 meters. Now I had a student in one of the classes, Kiera, who went beyond this a little bit and took not only this view, but did the table view, went to Control T and got a split table view. And using the table view, at 3 seconds we have 60 meters, and likewise at 4 seconds we have 60 meters. The thing with this table, the limitation of the table, is the table does not show to the half second between 3 seconds and 4 seconds. So it doesn't show 3.5 seconds, and 3.5 seconds will give 61, a height of 61.25 meters, which is close to 61 meters. So table view has its limitations. Yeah, we could go and change the table settings, and changing the table settings, where we do that table, edit table settings, we can go table step, we can go to 0.5 here. If we go to 0.5 and tab down, we would see, in this case, let's go down where it was. Here we go, going by 1.5 seconds. And here we have 3.5 seconds, just 3.5 seconds, we're showing 61.25 meters in height. So let's go ahead with our next problem, problem 5. The graph of the function h of x equals negative 1/3 x cubed is shown below. Which of the following is true? This is really a kind of a process elimination problem. Now, if we look at A, h of x is unbounded. That looks like it's probably maybe a good answer. Let's check the other ones out just to be sure. B, the function is increasing with an interval negative infinity to infinity. Well, in fact, the function is decreasing from negative infinity to infinity, so that would disqualify B from the right answer. C, h of x is symmetric about the y-axis. Well, here we have the y-axis. Okay, does this function demonstrate symmetry across that y-axis? No, it does not. And finally, D, the limit as h of x, as x goes to negative infinity, is negative infinity. Well, if we go toward negative infinity, we are not going to negative infinity, but rather to positive infinity. So D would be disqualified. Yes, A is the correct answer. The function is unbounded. The function is not bounded above, nor is it bounded below. A is the correct answer. Go on to problem 6. Which of the following best describes the function g of x equals x squared minus 9 over x plus 3? And we have a variety of answers. And so let's just go and graph this function. We can analyze, we'll analyze without graphing too. But to analyze this graph, I have previously graphed here this function f of x equals x squared minus 9 over x plus 3. And we do not see anything that looks like a discontinuity, meaning that this is not going to be probably an infinite discontinuity, but rather, if anything, a point discontinuity. And to check that, we're going to go to our table view. I'm going to go to press Control T. Now we were to the half, on the half here last, but it goes to an original table view. And here we see that we have undefined here at x equals negative 3. At x equals 3, we have no discontinuities. Function looks fine. And so the discontinuity is right down here, and that's going to be a point discontinuity. And basically, what it looks like is this. Okay, the point discontinuity would be, I'm going to draw it in blue, right here at x equals negative 3. We would represent this point discontinuity by an open point right here where x equals 3. So that's going to be our answer, which is Point discontinuity at x equals -3, answer B. Next we go to 7. Oh, this shows the an overlay of where this was when we looked at it earlier. Okay, we'll go to, oh, I did want to show this analytically, what happens. In the top, we have x squared minus 9 is quantity x plus 3 times quantity x minus 3, and we have over x plus 3, and our cancellation is this, and so this discontinuity at x equals -3 is what we call a removable discontinuity or point discontinuity. So the function has every appearance of being g of x equals x minus 3, except for that point discontinuity where x equals -3. Okay, again, B is our correct answer for 6. 7, if f of x equals x squared plus 2x minus 15 over x squared plus x minus 12, then f of x has a vertical asymptote at, and we have the different choices here. Well, we go to our graphing calculator, and again, I have previously graphed this function right here, and if we look here, it looks like the discontinuity is going to be approximately at x equals -4. We see it, and we can only confirm, we hope, if we go to Control T, we see a point discontinuity where x equals 3 that is undefined but does not look like any kind of discontinuity on the graph. But we go to where x equals 4, we see the discontinuity, the vertical discontinuity, and so for this problem, D is our correct answer. X equals -4 is the equation for our vertical asymptote. Now, problem 8. Which of the following graphs is the inverse of f of x equals 4x minus 4? And so, basically what we can do is we could graph the function f of x equals 4x minus 4, which here's your, if we did it over on this one, we would have, on A, we would have our y-intercept at y equals -4, and this slope, this rather steep slope of 4 or so. That's probably about right. And so what we're looking for is the function that would reflect about this line y equals x. And so we're going to be looking for a function that is down here, kind of like this. And the only one that could remotely be like that would be B. So B is probably our correct answer. Let's go ahead and use our analysis that we've done before in class. We change this function to y equals 4x minus 4. That's step 1. Step 2, we change the x and y positions. X equals 4y minus 4. Next step, we solve for y, add 4 to both sides of the equation. And so we have cancellation here. So we have 4y equals x plus 4. And so dividing both sides of the equation by 4, we have y equals 1/4 x plus 4 over 4 is 1. So here we have an approximate y-intercept of 1. This is definitely a slope of approximately 1/4. So B is our correct answer for number 8. 9, the function shown below has 2 real roots. No, I count 4 roots here, real roots, 1, 2, 3, 4. So we know that's not right. Is increasing over -2 to 4. Well, here's x equals -2 to 4 over here is increasing. Well, the function is decreasing here, and then increasing from about 1 on. So the function's not increasing over that entire interval, has at least one imaginary root. Well, we don't know that for sure, but we do know that we have a relative maximum here, a relative maximum here, and a relative minimum here. So 2 maxima, which is Latin plural for maximum, and 1 minimum, and B is our correct answer. Problem 10. What value or values are excluded from the domain of the function graph below? Well, we don't see any open points at all. We see only a vertical asymptote. And right here, it looks like at x equals -4 approximately, x equals -4, that looks like that's going to be our vertical asymptote, or the value -4 is excluded from the domain, the x value. So D is our correct answer. And finally, problem 11. Which of the following is the parent function of the graph given below? And really, it's a matter of graphing this in your calculator. If we drew 1 over x, answer A, we'd be looking like this. That would be a parent function. Nothing at all like that. If we looked at the square root of x would look like this. Again, nothing at all like we see on the graph. Answer D, y equals x, it would just be, or f of x equals x would be this. We see nothing like this. No, if we graph in the calculator this parent function here, we would see this type of V right here at the origin. So C is our correct answer. The one question I had a few times today was, how do you create that on your graph? Well, we're going to go ahead and graph that function by going to this little button next to the 9, and then to this button here. These are your absolute value brackets. We put our x there, press enter, and so we have the absolute value parent function touching down at the origin. So I hope this has been a helpful review. I thank you very much for viewing, and take care. Bye now.